Thank you, Dr. Araya, for the very, very kind invitation. It's a pleasure to be here. Also, thank you to the D. Howard Fellowship or Foundation for providing this opportunity to me. So I'll tell you about a project that we've been involved in for about 2 years now. We're coming close to the 24-month mark. The objective of the project is to use machine learning to improve what are called turbulence closures for the large eddy simulation of a very special class of turbulent flows. Those are called metastable turbulent flows. And I have a few slides to explain what those are. So before I get into the details of, let's see. Before I get into the details of the technical talk, I wanted to tell you a little bit more about what I do in my research group. Generally speaking, we deal with fundamentals of turbulence, mostly turbulent mixing, which is a fundamental process in any kind of technical device, as well as atmospheric flow. Of late, we've become quite interested in studying the combustion of ammonia and hydrogen, ammonia being a different fuel. This is work that is fundamental in nature, sponsored by the NSF. I've been involved also in the simulation and modeling and theory of low temperature plasmas. Those are a special kind of plasma that offers promise for efficient ignition of reactive mixtures. So especially in situations such as high-speed flows, think of scramjets where you want to anchor the burning flame to the cavity. These kind of plasmas offer an opportunity to do so. That was sponsored by the NSF and the Department of Energy. We also have an ongoing project. This is with Noel Clements. He does the experiments, we do the simulations. The idea is to come up with an improved framework to model the thermomechanical coupled performance of me, and it's in the hypersonic space. So when you're flying really fast, you want to make sure that you're protecting leading surfaces, nose cones, leading edges if you want to keep aerodynamic performance. How do you do that? You need a special class of materials, typically of composites. And so we are figuring out how to better model the coupled mechanical and thermal response of these materials. And finally, what I'm going to tell you about today, which is to use a technique in machine learning called reinforcement learning in the context of LES. And the idea is to use machine learning only from experimental data, with the idea that if you have a lot of experimental data, you should use it to improve modeling in the context of LES. All right, so today I'll tell you about this DARPA project we've been on. I'm here at UT Austin. I am the lead of the project, but I'm working with 3 other universities. And so I'll show you, for the most part, our work, but you'll see here and there also, to provide context, the work of our collaborators. This has been an amazing journey. I've worked with some excellent people. There is Petro Koumoutsakos at Harvard. He has a postdoc there, Quentin. He's working with us. At Hopkins, I'm working with Charles Meneveau and Greg Eink, and Shualin is the postdoc. And finally, I'll close with some final words and some conclusions. All right, so what is a metastable turbulent flow? So let's start with the definition. So it's a flow that appears to be statistically stationary, so it's still a turbulent flow, but it appears to not change macroscopically. And it's a configuration, a metastable state is a configuration that persists for a very, very long time. So if you're used to timescales in turbulence, you may think that a long scale in turbulence is an eddy turnover time. Well, those are states that persist for thousands of eddy turnover times, right? However, those macroscopic flows are not the true long-term equilibrium of the system. The flow just gets stuck in a specific configuration. Now, these things happen, for example, in wake regions of flows. So if you look at here, an experiment that was published in JFM in 2013 is a great example. Imagine you put what looks like a lorry or a semi in a wind tunnel, and then you do some sort of velocimetry in the wake. Imagine you're looking down on the XY plane. Here's what you would see, right? You would see in the mean 2 recirculation zones, right? That's the mean flow. However, if you were to characterize, so what you're looking at here is the Y z components. So this would be a plane that is orthogonal to the streamwise direction. And this is, if you will, an instantaneous picture, an instantaneous snapshot of the streamwise velocity. So red is coming out of the plane, yellow, it's back. So this would be your backflow in a classic wake flow. And imagine you're then determining it's centroid, right? And then you're plotting the y coordinate of the centroid in time. And what you would find is this kind of behavior, meaning the centroid is moved positive, so it's the wake is on one side, and it stays on one side for a long time, and then all of a sudden it moves to the other side. In other words, the mean flow is actually quite unlikely. What is much more likely is a flipping between one wake on one side and wake on the other side. This also happens all the time in strongly, massively separated flows on wings, where you have flapping of the separated regions, for example. If you were to do a PDF, you would see the PDF as being bimodal. You either see it above or you see it below. Okay. So what is a characterization? So what you can do, by the way, before saying anything else here, it's important to understand that when the flow is stuck in one of these metastable states, the metastable state is typically asymmetric, right? So we would expect the wake to be symmetric because the angle of attack, if you will, is the direction of the flow is symmetric with respect to the object. But in reality, these long-lived states are asymmetric. So we say that those break the geometrical symmetry of the configuration. So just to give you an idea of how long-lived, imagine we are observing here. I've zoomed up. I have provided you with a zoomed up view. Here's the wake is on one side, the positive state, and then all of a sudden it switches very rapidly. Those are very rapid transitions to the negative state. So it's now on the other side, and then it switches back again. We call the time the flow stays in this particular metastable state, we call it a dwell time. So if you were to calculate the eddy turnover time for this particular turbulent flow configuration, you would find that these dwell times are of order 500 to 1,000 eddy turnover times, right? So those are very, very long-lived states. Why does this matter? You can imagine that, for example, the drag is extremely sensitive to these, whether the flow is in state positive or state negative, right? Because, and the mean drag, if you will, is the convolution of the two states. Yeah? So actually knowing the two is quite important. Something a little bit closer to me, more metastable turbulent flows. This is a large eddy simulation we did a while back for the ammonia project. We're simulating a swirl injector on something you would find in a power generation system. And what you see here visualizes a low pressure region. This is called the precessing vortex core. And the precessing vortex core rotates very, very slowly compared to, say, the timescales of turbulence. And so you can imagine that such a system, such a large-scale feature, may determine whether, for example, you have a flame that looks like a V-shaped flame or an M-shaped, depending on where the flame is relative to the precessing vortex core. And this is really, really important for the performance. Yeah? So this is just to say that actually metastable states, metastable dynamics are actually probably the rule rather than the exception. All right, so in this project, we're focusing on a metastable turbulent flow that is amenable to experimentation, right? So we want to generate large amounts of data. So we use what's called the von Karman tabletop turbulence simulator, or VKTTS. So imagine a closed cylindrical vessel. You have an impeller at the top, you have an impeller at the bottom, you're spinning them. Those are impellers with 16 blades, they're curved, and one is spinning in one direction, the other is spinning in the other direction. Yeah. So what you're going to form here is a direct numerical simulation that we did at a fairly low Reynolds number. You see that the flow has very high turbulence intensity. And it's very convenient because what you can do is you can change the rotation frequency. You can change the mixture that you put in there. You can go with pure water, or you can do water and glycerol. So you can actually tailor and span the Reynolds number between 50 and about 1 million. So that really gives you the chance to test the validity of your closures over a very broad span of Reynolds numbers, which is always challenging. So the Reynolds number here is defined with the rotation frequency, which is the mean frequency between the two, the radius of the enclosure squared divided by the kinematic viscosity. And you'll hear me in this talk a lot about theta. What is theta? Theta, we call it a forcing parameter. So we take the difference between the two impeller speeds, and then we normalize it by twice the average impeller speed, right? So it's a dimensionless number. And when it's 0, it means you're spinning at the same rate. When it's 1 or -1, only one impeller is spinning. When it's slightly positive or slightly negative, you're biasing the forcing. And so you expect the mean flow to be asymmetric, right? So here I'm just going to play maybe a video just to give you an idea of what we're looking at. This is PIV from our colleague at Michigan. So, right, you have these two impellers that are spinning. Here you see the classic green glow of a green laser used in PIV. Now the impellers are going to stop and you get a chance of seeing this large-scale recirculations inside the fluid. So this is what we call a simulator. Of course, it's compact. We can do great things with PIV. Right, so let me just give you a slight overview before we get into the details. So imagine you're forcing the flow symmetrically. And here the color is the flow in and out of the plane. So blue would be in the plane, red would be out of the plane, and the opposite at the opposite blade. So clearly, if you force symmetrically, the mean flow is symmetric. You then increase the degree of asymmetry, so you slightly bias. This means that you're rotating the bottom impeller a little bit faster, and the mean flow starts to move. The stagnation plane here starts to move down. You bias it even more, it moves even further down. And then if you only move the bottom impeller, then you have what it's usually referred to as a one-cell flow. So how do you actually characterize macroscopically the state of the flow? You'll hear me talk a lot about the state. You need an integral quantity that tells you whether your flow looks more like this or more like this. And we follow the literature and we use what's called an order parameter. And what is that? That's a fancy way of calling the volume averaged angular momentum, right? So what you take is the azimuthal velocity, that's the component that tells you about the rotation. You multiply it by the radial distance and you integrate over the volume. In reality, because you only have a PIV plane, you integrate on a plane, not quite a volume. And this is different at different instants. If it's positive, and large positive, it means that the flow is going to look the opposite of how it looks here. If it's large and negative, it's going to look just like here. Right? It really, since it's biased by the radial distance, it's actually picking up the azimuthal velocity near the wall. So it's telling you which direction the fluid is spinning over most of the domain. Yeah? All right, so you do that, and you do that because you do that in a turbulent flow, so you expect things not to be quite steady. So you do that at, say, 900,000, and you're forcing symmetrically. You see this blue line here is the instantaneous value of this mean angular momentum. You do its PDF, and what you find, this is the blue line. What you find in the blue line is that it's centered and it's unimodal. Yeah? So notice that the most likely value is 0. Because you're forcing symmetrically, you expect it to be 0 as the most likely value, and the mean is also 0. You redo the same experiment at 40,000, so you're dropping the Reynolds number. You're still forcing symmetrically, and this is important. And yet what you find is that sometimes you find a positive order parameter. The fluid is mostly spinning one direction, and other times is mostly spinning in the other direction. We call this, again, metastability. This is very similar to what I showed you for the wake dynamics. If you then do the PDF, you'll find that the PDF is now bimodal. Sometimes it's spinning positive, sometimes it's spinning negative, and sometimes you even see the 0 state, right? The symmetric state. Notice that we're still forcing symmetrically. That means that the flow undergoes this long-lived reconfiguration. So the question now is, can LES capture this? Right? Will LES capture this? We need a little bit more of quantitative definitions. So I'm going to introduce two concepts. One is called susceptibility, and the other is called criticality. And the two are intimately related. So what do I mean by susceptibility? So imagine you're plotting the mean of the order parameter. So that's the mean angular momentum versus theta. Theta tells you how much you are forcing asymmetrically. So if you're forcing symmetrically, theta is 0, you expect the mean to be 0. That makes perfect sense. Then you start forcing asymmetrically. You start spinning one impeller a little bit faster than the other. And you would expect to introduce a bias in the mean angular momentum, and you do. However, if you notice, the sensitivity, which is the slope of these lines, right? The sensitivity of the order parameter, the mean order parameter here, to the change in forcing is significantly different whether you are at low Reynolds or high Reynolds. In other words, there are specific Reynolds numbers where the flow is very, very, very sensitive to the forcing asymmetry. We call that an increase in susceptibility. Yeah? So if you want to formalize it, you take the derivative of the order parameter with respect to the forcing, and this derivative becomes infinity near what's called a criticality. So here's that derivative. So remember, I showed you 900,000 and then I showed you 70,000. You notice that the 70,000 or 67,000 is steeper than the blue one, meaning there is a stronger susceptibility. The flow is just more sensitive to the forcing asymmetry. And notice here there is an asymptote. So the question really is that we sought out to answer with this project is, can we improve LES models to a point where we train the LES here at 900,000, the closures, the machine learning informed closures have never seen the criticality. The question is, will the LES be able to predict the criticality? Right? That is a very, very tall order, we believe. All right, so how do we go about this? So we first need data. And as I mentioned, we need a lot of data because we're going to do machine learning on it. And so what you see here are various iterations of what we call the von Karman simulator, or VKTTS. All of this work is done by Mirko Gamba at the University of Michigan. You see here the second iteration of the machine. He went for a monolithic optical grade acrylic enclosure where they carved out a cylindrical cavity. That's where the fluid is. Then there are impellers that spin at the top and the bottom. This gives him 360 degrees access, so he can do PIV on different planes. He can even do volumetric tomographic PIV, which is what he's about to do. We then went to a third iteration of the machine. We call it the Mark III, and that is improved because we're actually able to control the angular speed much more tightly than we were able to with the first iteration. Remember, we're trying to spin the wheels differentially. And so we really got to make sure that we know at which speed we're spinning, and we want the angular speed to be stable in time. These are also much larger motors, which means that we can actually spin faster and we can broaden the range of Reynolds numbers that we can cover. Here's again an example. What does he do? He does what's called three-component PIV. You've already seen this movie. I'll play it again. It's a three-component PIV on a meridional plane. So you have in forward scattering mode. So you have a laser beam that comes in. It's on the meridional plane. So think of a plane that cuts through the axis. And he has two cameras that are looking at angles that are optimal for backscatter. And he also uses fluorescent particles. Reason being is that there's a lot of scattering from bubbles, from surfaces and whatnot. So he hits the bubbles in the green, they fluoresce in the red. So he then detects with the interference filter, so he can only get the luminescence from the particles. He was able to achieve unprecedented levels of resolution. He's extremely good at what he does. And so he's down now to about 1 millimeter in resolution and 0.5 millimeter in spatial sampling. And notice this is about 200 millimeters, right? So we actually have a lot of data on a single plane, which is great for reinforcement learning. So here is an example of the kind of PIVs that you would see. So the color here is the in and out component. So blue, I believe, is out of the plane, our way, and red is into the plane. And the arrows are actually the velocity in the plane, yeah, the arrows. You can see how instantaneously the flow field looks like nothing like the mean, right? So notice how chaotic it is. And a classic turbulent flow, you have a variety of structures that are forming, some very, very strong stagnation regions that form throughout the layer. Pay attention to what's happening on the walls. You see that sometimes you see only red and sometimes you see only blue. That actually means that the layers are pulsating up and down, right? And this is precisely what the order parameter is picking up. So do we see these transitions? Yes, we do. So what you're looking at here is a time sequence, is a vignette. These PIV were done at high speed. They were done at 1,000 hertz, so 1 kilohertz. You can also run it at 1 kilohertz or down to 10 hertz to either sample for very long times or do it rapidly. And so here's a metastable transition event. So you're starting, but the false color here, the red, is actually no longer the in and out of plane. The red is the axial component. So red here means flow up, blue means flow down. So you see here that at this point in time, the flow is up. So although we're forcing symmetrically, you have that the top half of the fluid has been squished near the top impeller. Yep. But then as you wait, something happens over about 10 rotations. Now the blue portion, which is a downwash, has actually pushed back down to the bottom. One thing that is quite interesting is that this happens synchronously on the left and on the right sides. So there is actually a coordination. This is not the only transition we've observed. We've actually observed also one where the one goes up and the other goes down. We call that a symmetry preserving, for reasons that maybe we can get into if there is interest. And this would be what's called a symmetry breaking transition. Those are the ones responsible for that bimodality of the order parameter that you've seen. This is like a wake flapping, if you will. Right, so if you were to plot a parameter that tells you whether the fluid is all up or all down, this is what you're seeing here. The time is normalized by frequency, so you're reading directly rotations. Notice that those are 800 rotations, right? So you got to observe the fluid flow for a very long time. You can see that sometimes you're up, sometimes you're down, sometimes you're up, sometimes you're down, and so forth and so on. And these transitions are very fast. Notice these data were taken for the 300,000. And at 300,000, the susceptibility is still fairly mild and benign. We're now moving much closer to the criticality. All right, so now let's talk about what we do simulation-wise. So this is just a slide that recaps the equations that we're solving. I'm sure a number of you in the audience are going to be familiar with the large eddy simulation framework. You start off with a random field here, F. You filter it, although the filtering is implicit, and just for the sake of deriving the equations, you get a filtered field F bar. F bar allows you to decompose the instantaneous random field into a filtered field plus the remainder, what we call the fluctuation. We're then solving for continuity, for the filtered velocity, and we're solving for the three components of momentum in a filtered sense. We always work in dimensionless form, so viscosity is 1 over the Reynolds number. So as the Reynolds number increases, the viscous term is becoming multiplied by a coefficient that is smaller and smaller. Of course, closure-wise, you're stuck with a subgrid scale tensor, which we call the tau ij SGS. Our closure is a classic Boussinesque type closure, where the deviatoric part of the subgrid scale tensor is thought of as being equal to the filtered value of the rate of strain tensor multiplied by the eddy viscosity with a 2 for historical reasons. Nu T is the turbulent eddy viscosity. We close it with a Smagorinsky closure, where CS is the Smagorinsky coefficient, which ends up being computed using what's called the dynamic Germano closure. Now, we add something else, which is called the Lagrangian filtering. meaning this CS, these filtered quantities, Lij and Mij, are actually also averaged in space. This goes back to the work of Charles Menneveau at Hopkins in the 90s. Right, so the first problem we had to solve and we had to use machine learning for was, so how in the world are we going to model the impellers, right? So the LES is very coarse. Why do we need a very coarse LES? Well, first of all, we want to make sure we want to run for thousands of rotations, which means that we cannot have a very expensive LES. We need an LES that is very coarse because we want to simulate the flow cheaply. We need to integrate over thousands of rotations, so our LES must be cheap. So there is no way we can actually resolve the geometry of the impellers. What we do actually is to use what's called a penalty forcing method. What we do is we add a body force to the momentum equation, and that body force is only added where the impellers are physically in the domain. Yep. And then we need to figure out how the body force looks like. For us, it looks like a penalty method where the body force is proportional to the difference between the instantaneous LES field and the velocity we actually want. And so the force is always trying to restore the velocity to the velocity we want. Now notice that for dimensional consistency, the consistency alpha is a rate. So it's a 1/time. That tells us how fast we're actually restoring. We set that to about a time scale consistent with 1 rotation. So we want that within 1 rotation, we reestablish the correct velocity. Who gives us the velocity? Well, we write out the velocity in terms of B-splines. So those are just piecewise polynomials in both the radial and axial directions. And then we use what's called the covariance matrix adaptation evolution strategy, or CMA-ES for evolution strategy, to optimize them with the objective of minimizing the difference between the mean flow we get from LES and the mean flow we get from experimental data. As you can see, by the time the two are optimized, we get that one is equal to the other, and the relative mean error is very low. The mean is about 19. Notice that the relative error, which is the absolute error divided by the local mean velocity, is large near the stagnation points near the wall and the center line, simply because the velocities are very low at these points. And so we get a more of a ballooning of the relative error. But I think we can all agree that this was actually a big success in the sense of learning directly from PIV how to actually force the impellers. The second thing we need to do is to do wall modeling, right? So this is very coarse. So there's actually no way we can resolve the turbulent boundary layer. We are at, say, Reynolds of 600, 700, 800,000. These boundary layers are very thin. And so what we do is we use what's called an equilibrium wall model. So what we do is we assume that the wall stress propagates through the entire boundary layer. And so the fluid is effectively in force equilibrium with respect to the stress exerted by the wall onto the fluid. If you do that, Charles Menneveau showed that you can actually parameterize the solution to this simple ODE in the direction normal to the wall. And you can then recall what the stresses should be like. RE delta here is the velocity from the instantaneous velocity from the LES at 1 grid point off the wall. So we are in the fluid, 1 grid point off. Delta Y is the distance, that distance of the grid point. And nu is the kinematic viscosity of the fluid. So instantaneously, we calculate RE delta. We get into this table. We query this table. And once we have that table queried, we get back what's truly a dimensional viscous velocity here, friction velocity. And we then use that friction velocity to impose the correct boundary conditions. This actually works quite well. This is just to show you that the first point in the LES, by our estimate, is fully in the log law region. So we're very far away from seeing any kind of velocity gradient near the wall. So to us, really, the wall is not really a wall. It's just the end of our computational domain. The wall dynamics are never really seen. It turns out this was actually very, very important to do. Early on, we did not have a wall model. And without a wall model, we were actually not seeing metastable state transitions, as I'll show you in a moment. We added the wall model, and the wall model was instrumental in actually causing these transitions. Does this work? It works quite well. Here you see three components of velocity, the azimuthal component, the axial component, and the radial component at three different axial locations, plotted as a function of the radial distance. Bottom line is that the symbols are the experiments, the red lines are the LES. The agreement is really good. Now, of course, we're forcing it with the impeller. So by definition, we're recovering something that looks very good. So that means that the mean flow is captured very, very well. Notice that this is a fairly unresolved LES. 36 grid points in the radial direction, 64 in the axial direction, and about 56 azimutally, right? So those are fully 3D simulations. So here's an example of what we see LES-wise. Again, this is on the meridional plane. So we're taking a cut that contains the axis. And you can see here, again, the axial velocity plotted on the meridional plane. You see the usual downwash in blue and upwash in red. And here is a cut on a plane that is actually normal to the axis. And I'm plotting the axial velocity, the azimuthal velocity. You see a lot of stirring, right? This is the action of the impellers that puts the fluid into motion. So do we actually capture the bimodality? We do. So here's the results of here's the order parameter. So this is the same order parameter that you've seen from experiments. It's plotted as a function of rotations. Here you see we had to go all the way to 3,000 rotations to be able to actually converge the PDF of the order parameter, right? And the reason is because if you don't average over very, very long periods of time, you may only see one of the two states. If you want to capture and converge the PDF of both, then you need to observe both, which means that you got to integrate for thousands and thousands of rotations, which of course is time consuming. You see here the PDF, it has two distinct peaks, an A peak and a B peak. I is positive in the B state, I is negative in the A state. What you can then do is you can conditional average, meaning you only accumulate the mean when the order parameter is positive or negative, and the following picture emerges, whereby in one case the flow is down, and in the other case the flow is up. So by conditionally averaging, you're isolating these two states. Right? Of course, to conditional average, you do need enough statistics in either of these states. Otherwise, things are going to get noisy. And you can kind of gather that by the fact that this mean looks a bit less converged than this one. And this has to do with the fact that state B is a little bit less prevalent in this particular configuration. So we saw just less of it. And so it's less converged. Notice that if you now look on this plane, the plane that is normal to the axis, and red is still flow up. So you see this is flow up and this is flow down. And you see in state B, flow up now has shifted by 90 degrees. So it actually turns out that what you're actually seeing on this meridional plane are actually rotating azimuthal modes, which is actually quite interesting and largely unexpected. The interesting aspect here is the fact that we can now ask the question, how long does the flow stay in state B and then in state A? And it turns out that the dwell times in each of these states follow an exponential distribution. So we're actually able to recover also the mean dwell time due to the, as explained by an exponential distribution. As I mentioned before, we did this exact simulation without a wall model. The bimodality disappears. So it turns out actually that the dynamics of the boundary layers on the outer cylinder are key to engendering this switching, these transitions between the two metastable states. So here's another movie. So because we were quite excited to see this strong azimuthal bimodality and wave numbers, we said, okay, how about we plot and we look at a movie where we sample one grid point off the wall. So we're very close to the cylindrical enclosure. And imagine you take the cylindrical enclosure and you unwrap it in the azimuthal direction, right? So what we're really looking at is the flow that swirls around the cylindrical enclosure. I'm going to show you three things. So here's the axial velocity. This is the azimuthal velocity. And this is the magnitude of the two. Remember, axial and azimuthal are the tangential components to the wall. Yeah? So if you now play that, you see that on the left-hand side, it's going to go for a while. This is, again, I think at 300,000. And what you can see here, this very large engulfment. So as expected, at the bottom impeller, you're dragging the fluid to the right. At the top impeller, you're dragging it to the left. This is expected. This is just the action of the impellers. But you see here that in the tangential velocity magnitude, you form this low speed region where the stagnation plane is, right? So that's a region where the flow stagnates. But notice how the flow, the fluid is actually, the velocity is actually organizing itself in modes. If you now take this instantaneous movie and you average over about 50 rotations, what you'll find is these azimuthal modes where the fluid goes from faster to slower, with a wave number of about 2. Now, that's interesting. Why does it appear? Why is it 2 instead of 4 or 3 and so forth and so on? We believe that this is very, very much Reynolds dependent. Interestingly, people have seen this at Reynolds number of 500. So think about that. You see the same patterns in the mean averaged over 50 rotations, which is very long for eddy turnover times, but very short for long-term observations. You see the same patterns at Reynolds of 500 as you see at a Reynolds of 300,000. Right? So there is something inherent about this organization. Right, so the last thing I'm going to tell you about is what we're doing now with reinforcement learning. And this is all work that is done at Harvard University. We're applying a technique that is called reinforcement learning. So what is the reinforcement learning? Let's read the Wikipedia definition. It's an interdisciplinary area of machine learning and optimal control that is concerned with how an agent should take actions in a dynamic environment to maximize the cumulative reward, right? So this is a little bit like what you do when you're learning something new. Suppose the agent is the biker. Suppose the action is pedaling, steering, right? Shifting your balance. And what you are doing, you're observing the environment around you. You know where you are. You know you need to take a turn. You know how tilted you are, perhaps, right? You have a sense of your state. And what you want is to maximize a reward. And the reward for you could be, I want to be able to take that turn as fast as I can, right? So by learning, what you're going to do is you're going to learn what actions you need to take to satisfy your reward. If this feels a lot like optimal control, well, because it really is. Reinforcement learning can be interpreted, in fact, as an optimal control. So here's what I said. There is an agent, there is an action. The action changes the environment. The agent observes the state and tries to maximize a reward. This is the reinforcement learning loop. For us, the reward is based on experimental data, meaning does our simulation match experimental data? The action is going to take the form of a wall model that improves the simulation of these metastable states. And the state is going to have to do with something related to how does the flow field look like near the wall? Yeah. And the reward, of course, has to do also with predicting susceptibility. In practice, if you want to anchor your thoughts to equations, what you're doing is that you're taking a system of equations. These could be differential equations, it could be algebraic equations, and you're putting in a source term. And that source term looks a lot like the actuation in a controlled system, right? This is your force or your torque on the motor. This is your actuation. And what you want to do is you want to learn a policy such that given the state, it gives you an action, right? So effectively, you're trying to change the dynamics of the system to make the system do what you want it to do. Yeah? So in our case, we use what's called a multi-agent reinforcement learning. Here is shown for homogeneous isotropic turbulence, where you have say a turbulence box. This is a box of fluid turbulence. You scatter a bunch of agents. That's why it's called a multi-agent. The agents here are observing the state. So what is the state? The state is a combination of global variables, for example, the spectrum of turbulence inside the box, or maybe you have the total dissipation of kinetic energy in the box. This is the state instantaneously. Then the agents may also observe something local. For example, the agent observes the eigenvalues of the resolved rate of strain, velocity gradient tensor. And based on the observation, they take an action. And the action in this particular example was setting the eddy viscosity. Right? So they set the eddy viscosity. They know what the local gradients are. They know what the total dissipation in the box is, and they decide what the eddy viscosity should be at where they are located. Because they're located at discrete points, you then interpolate these different values of eddy viscosity. You need it everywhere in your LES domain. And then you take a step. What is the reward? You can use local measures. You can use global measures. Right? This is the beauty of reinforcement learning. The reward really can be whatever you want it to be. If you want it to be local, for example, I want to be able to reproduce the gradients at that point, then you can make it so. However, you may want to make it global. For example, I want to be simulating correctly the spectrum of turbulence. Yeah? That's a perfectly legitimate reward. In our project, we're mostly concerned with the wall model. As I mentioned, the wall model is key to capturing these state transitions. So what we're going to do is, what we're actually doing right now is to pick the state as giving us information about the velocity at one grid point off the wall. So we're just going one grid point off the wall. We get the velocity and we get the gradient of velocity at that point. Based on that, we choose a multiplicative factor that is going to be multiplying the shear stress from the equilibrium wall model. So we're not throwing away the equilibrium wall model. We're just asking the reinforcement learning to correct it slightly. Right? So the idea is that the equilibrium model is pretty good, but if we want to correct it, well, we should correct it in a way that improves our outcomes. Notice that because the agents are scattered throughout the enclosure, in principle, the correction can be different at different places. Right? And that's a real advantage of this method. What is the reward? We use what's called the Kolmogorov-Smirnov distance. That's just the distance between functions. And what we want to minimize is the distance between that bimodal PDF that we measure experimentally and the bimodal PDF that our LES reproduces. In other words, we want to capture the phenomenology of the state switching, right? The frequency by which the two are switching. We also have what's called a spot reward. That's an additional reward, which is based on the dwell time. How long are we stuck in one state as opposed to being stuck in another state? We want to be able to capture those correctly. Right, so I'll conclude with so if all of this was somewhat exciting and you're thinking of maybe looking into turbulent metastable state flows, which in my view are everywhere, really, and I'll give you a couple of examples. It's more the norm than the exception, actually. And they're very important because depending on which state you're in, you end up with vastly different mixing, vastly different flame stabilization, vastly different drag. So it actually matters a lot. However, some words of caution. So the first thing is that those are very long-lived states, which means that they require very long experimental and computational observation. If you do simulations, you got to simulate these flows forever, which is computationally demanding. If you're an experimentalist, you got to take PIV forever, which is also experimentally demanding because maybe you can run the experiment a long time, but then when you post-process your images to get PIV data, you end up with terabytes of data and maybe 10,000 hours of PIV processing time, especially if you are in tomographic PIV or three-component PIV. So notice here that this PDF was taken over 20,000 rotations, right? So, or 1,800 seconds. Imagine you're going at 10 hertz, right? That's a lot of time, right? You're going to be stuck in the lab for a very long time. The other thing is that if you want to go after criticality, that's where the flow becomes really sensitive to the forcing. Then you must control the forcing very, very, very carefully. And that is very hard to do. So just to give you an example, this is a zoomed in version of the graph that I showed you before, where you are looking at the mean order parameter plotted as a function of the asymmetry forcing parameter. So 0 means that we're spinning them at the same rate. The mean order parameter, the mean angular momentum is 0. Fine. You start forcing them asymmetrically. One goes a little bit faster. Notice how the Reynolds of 65,000 near that criticality is much steeper than at 800,000. So if you are an experimentalist and you want to convince yourself that this is not just a fluke, you'd better control theta very, very carefully, because you got to know how much faster you're spinning compared to the two spinning at the same rate. So just to give you an idea, to go after these, we had to control the impellers to better than 0.1%, right? And so that means that these experiments are also computationally challenging because it's not just about forcing, it's also about geometry. So you got to do things very, very, very carefully. And finally, you are fair and square in the domain of statistical analysis. You can't just rely on the mean here to convince that the blue line is different from the red line. You need to put confidence intervals on those. And that means that you got to run from beginning to end all of these analyses in a statistical framework, right? Because the two tend to be, you gotta be able to distinguish the two. Yep. Right. So finally, some concluding remarks. So hopefully I've excited you with regard to turbulent metastable states. So those are my position here is that turbulent flows although I think it's a little bit too cautious. I think they often organize themselves in long-lived, large-scale coherent states. Sometimes they get referred to as geometries because they're truly different macro-scale flow configurations. Those reconfigurations or those geometries, those states, they break the symmetry of the flow configuration. However, the symmetry of the configuration is recovered in the mean. So if you're forcing symmetrically, your mean is symmetric, but the flow spends in asymmetric states an awful long time. Yep. The geometry of these metastable states is often qualitatively similar to that of what are called bifurcated flows at much lower Reynolds numbers, which to me, it's very exciting. If you think about it, how come these large rollers look the same at 500, a Reynolds of 500 as they do at 900,000? And that's quite remarkable that this imprint, this very specific structure persists over this enormous range of Reynolds numbers. So the dynamics of these structures is highly consequential because it governs mixing, it governs stability, it governs drag. Yet it is very difficult to model, it is very difficult to analyze, and it displays exquisite sensitivities to boundary conditions, right? So they're hard to study. Two examples, they are planetary examples. I am in an aerospace engineering department after all. We have a lot of people that work on satellite sensing for the atmosphere. Classic example, Earth's global circulation has these large-scale persistent structures, these cells. And these cells are there. They stay there. Why are they there? Well, some are cautioning that should the position of these cells, and they shift slightly during the year, the position shifts slightly, and that's responsible for altering the global circulation patterns. Now, one question that people have asked is what happens if two cells merge, right? There is no fundamental reason why there should be as many cells as there are. After all, the Earth is more or less a sphere. Why are there as many cells as there are? Why are they going to merge? Is one going to disappear? And so forth and so on. Those are very fundamental questions, especially because they govern the long-term climate of Earth. So metastable flows are here. If you're more into astrophysics and sky watching, very fascinating. When I was at Berkeley, Philip Marcus studied a lot the Great Red Spot. If you're curious, you can pick up his papers. Amazing discussion of why this feature in the Jovian atmosphere is so persistent. People have observed it for 200 years. You have early astronomers sketching the red spot. And here I'm going to show you this amazing picture of Voyager 1 a long time ago. That's about 46 years ago, where you can clearly see the great red spot as Voyager was coming closer to Jupiter. taken over about 60 days. This is a feature that persists. It is clearly breaking the symmetry of what is a spherical system. We understand jet streams, right? The planet is spinning, but why is this symmetry breaking structure stuck there? And is it going to go away? It seems pretty stable. Doesn't seem to be going everywhere, but maybe it's going to go away in 10,000 years, 100,000 years, who knows, right? But certainly it's very stable compared to, say, the eddy turnover times over one rotation. You can imagine here that our eddies shedding from the jet streams, that's very, very fast compared to how long the red spot has actually lived. So why is it there? So I'll leave you with that, and be happy to take any questions.